All right, so all we're going to look at today is we're going to just wrap up the stuff on the rational root theorem. Okay. Last time we talked about Descartes' rule of signs, and you got a little practice with that. Remember, all that does is it just gives us the possible numbers of positive real zeros. So if we were to graph it, real zeros correspond to x-intercepts. So those would be positive x-intercepts, and then the negative real zeros, so the negative x-intercepts. Okay. Can you hear me okay, Maria? Okay, good. All right. Today we're going to add something a little different, and I want to give you a conceptual backing for this. There's a way that you can, this is the way I show people, kind of give them a little insight into why this rational root theorem works. I'm going to take you through two quick examples. And then, yeah. Is it not? You can't hear me?
It's not presenting.
Oh, whoops. Oh, okay. Gotcha. There we go. There. Is that better?
Yeah.
Okay. Yeah, you betcha. Okay, so give you a little insight into why this rational root theorem, I'm going to show you why it works. So let's start with some of the stuff we were doing in the last section, where if I give you zeros, you can construct a function from the zeros, right? By just using the factor theorem. We know that zeros always correspond to factors. And so we've done this a bunch of times. If my zeros are 5, -6, and 12, then we know that the corresponding factors are x minus 5, x plus 6, and x minus 12, okay? Notice, just for later reference, that the coefficients of x are all 1, right? When I multiply those out, what happens? Well, if I go through that whole process, I end up with this polynomial, x cubed minus 11x squared minus 42x plus 360. Okay, well, how come we got a 1 in front of the x cubed? Because, would you agree it's because all the coefficients of x were 1, right? And how come we got a 360 for our constant? Because that's the product of all of those values of k. Everybody agree? Okay, all right. So then what if I wanted you to work backwards and find all the rational zeros or all the rational roots of this function? Okay, we'll come back to that in a second. Let's look at one more example. How about one like this? What if my zeros are fractions? 5/2, -6/5, and 10/9. Okay, so then the factors would just become x minus 5/2, x plus 6/5, and x minus 10/9, right? And let's say that those are the zeros, right? So I should be able to actually set this whole thing equal to 0, and that should be a true equation, right? So if we want to find a more convenient expression for this function, then I could clear all those fractions, couldn't I? Right? Like I could multiply each side by 2. If I multiply each side by 2, that's going to give me a 2x minus 5, agreed? Now, and I don't distribute that 2. If I'm multiplying 2 times the first factor times the second factor, when I multiply things, I just multiply in pairs. So if I multiply the whole thing by 2, the 2 is really just getting multiplied by this first factor, which changes the first factor, but then we just continue to multiply by the other ones unchanged. Agreed? If I want to clear all those fractions, wouldn't I have to multiply both sides by 2, n by 5, n by 9? But 0 times anything is 0, right? So really all I'm doing then is if I clear the fractions by multiplying through by 90 in this case, that's just going to give me a 2 here, a 5 there, and a 9 there is all, right? Agreed? So I've got those written without fractions now. But the zeros are still the same, aren't they? The 0 of 2x minus 5 is still 5/2. The 0 of 5x plus 6 is still -6/5, etc. Right? So we haven't changed. I mean, we're still coming up with a polynomial, but we're just coming up with a more convenient polynomial. Now when we distribute all this out, our polynomial is not going to have a bunch of fractions, right? Alternatively, what I could have done, and this would have been messy, I could have just expanded this whole thing out and gotten a whole slew of fractions, right? And then I could have cleared the fractions by finding the least common denominator of all the fractions. Well, what would it have been if I had done that? If I had just multiplied this whole thing out and gotten an x cubed, well, my first term would have been x cubed, and then I would have just gotten fractions in the rest of them. To clear those fractions, what would I have had to, I guarantee you could tell me right now, what number would I have had to multiply both sides by to clear all those ugly fractions? 90. Agreed? Okay, we just did it in a more convenient way. We just did it before we multiplied everything out. Okay, give me thumbs on that. Everybody good with that idea? Okay, good. Good, good. All right, so then if I multiply this whole thing out, we're not going to go through that hassle. You can all do that. This is what we'd get. We'd get 90x cubed minus blah, 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 blah. We don't care. Plus 300 we do care about. We got the 90 because that's the product of 2 times 5 times 9. We got the 300 because that's the product of 5 times 6 times 10. Okay? Now look back at this here. Okay, what do you notice? This is kind of color-coded in an important way. My original zeros, do you see that the product of the denominators of the original zeros is what gave me the 90? Everybody get that? The product of the numerators of my zeros is what gave me the 300. Just like in the previous example, these zeros were all integers, and so the denominators were 1, right? But the same pattern holds. The product of the numerators gave me 360, and the product of the denominators gave me 1. Okay, so now how could I turn this around and work backwards with this problem and find all the rational zeros? You see a way that I could come up with maybe not the exact answers right away, but I could come up with a list of possible answers that I could check and extract the 3 correct zeros? What would have to be true if I just focus on the constant and the leading coefficient? How could I come up with a list of possible candidates that would definitely include all of those fractions that are the actual answers? You think, well, I take a roll, just think about that for a second. What do you think? Any ideas? I want to know, I mean, if I wanted to go to try to solve this equation with no hints, right? In the past, I would have given you, like last section, I would have probably given you one of those and helped you to find the other two, right? But now I'm not doing that. We've got to try to solve this, find the zeros of this cubic polynomial without any help at all, okay? And obviously, grouping's not going to work here, right? Because the ratios of the coefficients are not equal, the first two and the second two, right? So I want to know, how could I come up with a list, maybe a list of candidate zeros that I could just check. I could check each one to see if they actually are zeros. And it could be a long list, but I want to have a list that is for sure going to include, so eventually I will be able to find those in my list if I check them all. What do you think, Andrew?
You could do a list, like for the denominators, you could do a list of the 3 factors equal 90, and you multiply them all together.
Okay. Okay. So the denominators, and maybe I'll restate that slightly. The denominators would have to be factors of 90, wouldn't they? Agreed? Because we built the 90 by multiplying the denominators together. Agreed? The numerator, the numbers in the numerator would have to be factors of what? 300. You see that? That's the rational root theorem. That's it. Okay, the rational root theorem just states that all rational zeros can be written, so zeros that can be written as fractions, right, must be included in a list of fractions that we can build by dividing a factor of the constant by a factor of the leading coefficient. That's it, okay? So here's kind of a more of a textbook statement of that. What do you have to do? Given a polynomial function f of x, how would we use the rational root theorem to find the rational zeros? Determine all the factors of the constant term, make a list, and all the factors of the leading coefficient. And then we have to find what are all the fractions we could build from those, right? All the fractions that we could write as p over q, where p would be a factor of the constant and q would be a factor of the leading coefficient, okay? And then we'd have to just check them all. Determine which possible zeros are actual zeros by evaluating each one of those. But we could do that synthetically though, couldn't we? Right? Because we want to know if they're zeros, so we would just run them through synthetically until we get a zero in the remainder box, and then we got a hit, right? And if it's a cubic polynomial like this last example, how many do we really have to find using the rational root theorem before we can get the rest easily? I mean, there's 3 total. Right. You're correct, Maria. 1. How come? If I find 1, so right, if I find 1, then if I divide, really by using synthetic division, you know, synthetic division is doing 2 things at once. It's telling me if I get a 0 in the remainder box, it tells me it is a 0, but a 0 is also a factor, right? And so we could divide our original polynomial by that factor. And the other thing synthetic division gives us is the coefficients of the other factor. What's the degree of the other factor going to be once I find 1, 0? Yeah, it's cubic, right? So if I find 1, the other factor that's left over is going to be quadratic, and that's piece of cake, right? We can solve any quadratic equation easily. If nothing else, we can just use the quadratic formula, right, to get the other zeros. So we really only need to find 1. Once we get it down to a quadratic factor, it's essentially done, right? Okay, so let's try this. How about this one right here? I want you guys to pick which of those lists is the complete list of possible zeros for this function, possible rational zeros. You get that there's a little hole in this strategy. It doesn't always work because what if none of your zeros are rational, right? It's possible you could have a polynomial where none of them are rational, and then you're stuck. Then you can't find them this way, and you got to move on to something else. And the something else we would use it's called Newton's method, and it's a calculus approach, okay, which we're obviously not going to do. So which one of those lists, A, B, C, or D, would be the correct one? So let's figure it out. Let's make a list of candidates here, right? So if our zeros are going to be of the form P over Q, what are the possible values of P? P are the factors of what? Constant or the leading coefficient? Constant. Okay, so the P, what are the factors of -6? Or even just, you don't even have to include the negative sign because we're going to always include the positive and the negative. So aren't we going to get plus or minus 1? Keep going. Plus or minus 2, plus or minus 3, plus or minus 6, okay? And the denominator Q is 1. So the denominator could only be plus or minus 1, right? Dividing by 1 leaves us with integers, so what's our answer? Last one is D, isn't it? Right? I'm going to get plus or minus 1, 2, 3, or 6 divided by 1, right? In the denominator, I don't even need to include the plus or minus either because I've already got those in the numerator, right? That makes sense when you're doing this from a practical standpoint. So the answer is this guy. Okay, give me thumbs on that. Okay. Okay, let's do another one. Let's do another one. Yeah. Mm-hmm.
So we're not going to use Descartes' rule at all for that.
No, we can. We can use Descartes' rule of signs, absolutely, and we probably should, right? When we start to look for those things, that's a good point. So what does Descartes' rule of signs tell us here? What are the possible number of positive zeros? It's one, right? So it's only one. So we would know, that's helpful to us too, right? Because if we're going through our list, what if we get a positive zero? Let's pretend that this was a bigger polynomial, bigger than cubic, right? What if it was like a 7th degree polynomial or something, but it only had one positive zero? Well, once we find one positive one that works, I could cancel all the others off my list and not have to try them. You get that? So Descartes' rule of signs we can strategically deploy that, right, to make our workload a little smaller on the problem, okay? In this case, we don't really have to, though. Well, actually, I'll tell you what, the one thing we may need to do is we need to see if there's no sign changes. That would be helpful to know, right? But we could have at least one positive. What about negatives? If I take f of negative x, I'm going to get negative, positive, positive, negative. So I'm going to get either 2 or 0, right? That makes sense? Okay. So we still got to find, we're still going to have to find one of them. So in this case, it doesn't really help us a ton because we could have both a positive, we could either have a positive or a negative 0. Once we get one, we're done anyway, because then we'll just use the quadratic formula, right? Okay, let's try another one of these. Let's just practice finding the possible zeros using what are the candidates here? What's our list going to comprise? So we got factors of 6, positive and negative factors of 6 over factors of 3. So the denominator, unsimplified, if we not reducing the fractions, the denominator could either be 1 or 3, right? The numerator could either be 1, 2, 3, or 6. Anybody see that? So we're going to get, our fraction is going to be built like this. We're going to end up getting, what are our possible, what are the possible numbers we could get? On the top, we're going to get plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6, divided by, on the bottom, we could only have plus or minus 1 or plus or minus 3. Well, if we take the ones on the bottom, we're just going to get 1, 2, 3, and 6, right? If we take the 3 on the bottom, we're going to get 1/3, plus or minus 1/3, plus or minus 2/3, plus or minus 1, which we already have, or plus or minus 2, which we already have. So we don't need to include those twice, right? So then my list would just be, wouldn't it just be this guy, whoops, hang on, this guy right here, wouldn't it? Everybody see that? Okay. Okay, give me thumbs. Okay. Okay, that second example helped, yeah. All right, so let's use this thing. Let's actually do one of these guys, okay? So find all the real zeros of this polynomial. Man, I guess that's a little bigger than I thought it was going to be. Why don't I give myself a little more room? You guys can all see that okay, can't you? Okay. All right, so we only need to find one, and the others will be easy, right? So we need to find the possible candidates. So let's make our list of possible zeros. We're going to get zeros of, or factors of 10 over factors of 2. Okay, so the factors of 2 in the denominator are either 1 or 2, right? So if the denominator is 1, what values would I get then? Factors of 10 divided by 1 would be what? Whoops. So 1, negative 1, 2. Okay, and if we continue our list with 2 on the bottom, we'd get, these two are going to give me 1/2, -1/2. Those are giving me 1, and -1 I already have. 5/2, -5/2, and then 5 and -5, which I already have. Everybody agree? Okay, so we want to just start with the easy ones, obviously, right? Start with the low-hanging fruit, because those are easier to run through synthetically. So smaller integers would be the easiest ones to try first. Okay, so here's where we can use that tabular integration. This is where it's really, or not tabular integration, the tabular synthetic division that I kind of briefly showed you before, right? Where we write them all as a table. So if I want to write out the coefficients for synthetic division would just be 2, 3, -9, and -10, right? Okay. We're just going to make a bar out front, and then we'll try a candidate, and we'll run it through synthetically, and our goal is to see if we get in the remainder column now. It's not going to be a box anymore. In the remainder column, if we get a 0, we struck gold, right? Okay, so let's try this then. We've got our candidates up there. Let's try an easy one. Let's try something like 1. So if I run 1 through synthetically, now what I'm going to write here, this is going to be the coefficients that would be below our synthetic bracket. We're just going to do the mental math in our head. So we bring the 2 down. 1 times 2 is 2, plus 3 is 5. 1 times 5 is 5, plus -9 is -4, and that one's not going to work, is it? Everybody agree? So we can cross that off. 1 comes off the list. Okay, let's try -1. Get my 2. -2 plus 3 is 1. -1 plus -9 is -10. -1 times -10 is 10, plus 10 is 0. We got it. Okay, so we hit it on the second try. So -1 is a hit, and then what's left behind is the quadratic factor, right? So now we can just use the either factoring or the quadratic formula. Because a is not equal to 1, let's not even bother trying to factor it. Let's just use these values of a, b, and c and plug those directly into the quadratic formula. Everybody see that? Okay. So then to get the other zeros, we recognize that's a, that's b, that's c. And so we get x equals -b plus or minus the square root of b squared minus 4 times 2 times -10. And look, negative times negative gives us positive, right? Yep.
So if you had a quartic polynomial, would you need to find 2?
You would. Yeah, then you'd have to find 2, exactly. Yeah. Yeah, we'd have to find, once we get it down to 2, we're done because the quadratic formula we could use. But otherwise, you're right, we'd have to go through this multiple times. And so what we could do then, if we had to find another one, I would just put a line under this and make my remainder column be under the 10 now. Does that make sense? Okay. And then we just keep going. Now, okay, here's another question though. And we'll go through one like this at some point. But that -1, do I cross it off the list? Say this was quartic, and -1, I got a hit on -1. Do I cross it off? Say it again.
Well, it's still a 0.
It's a 0, but I mean, do I have to? So could I just skip that one and move on to the next one when I'm looking for another 0? It could have a multiplicity of more than 1, right? So I only cross a number off the list if it doesn't work. If it does work, and I have to try it again. If I've got a big polynomial where I've got to find more, I've got to do it again until it doesn't work, and then I cross it off. Everybody get that? Okay. All right, so divided by 2a, so divided by 4. There's my other answers, right? My other solutions. So what am I going to get? -1 plus or minus the square root of 81, which is 9, right? Plus or minus 9 over 4. So my other two zeros would be negative 10/4. So either x equals negative 5/2 or 2. Okay, everybody agree? Now notice that those were rational zeros, and they are on my list, right? They didn't have to be rational zeros. They could have been irrational, and then they wouldn't have been on my list. But if they're rational, they have to be on my list. Have to. Okay? Give me thumbs. Okay? All right, let's try something like that. So look, they gave us a little snapshot of a graphing calculator on this one to help us out. Okay, so where is that 0? Can you guys interpret that window there and tell me what the value of the 0 is that they're giving us? What is it? What's all this stuff mean down here? What's 0, 2.5, 0.25 mean? No? It's just telling me the window size. Here's what it's telling me. It's telling me that it's going from 0, whoops, right there, to 2.5 right there, and it's going in increments of 0.25. Okay, and then the other one is telling me that it's going from negative, so that's what this tells me. This guy here is telling me that it's going from negative 10, oh, come on. Oh, this is frustrating when it does this. There we go. Ah, I lost all my stuff though. Well, you get the idea. I'm not going to draw all that again. You get the idea though. It's just telling me that it's going from, it's giving me the width of the window. So those are the key numbers on the x-axis, and those are the key numbers on the y-axis, right? So it's going from 0 to 2.5 in increments of 0.25. Vertically, it goes from negative 10 to 10 by ones. The hash marks are by ones, okay? So then we can see that that must be at 2, right? 2.5 minus 5.5 would give me 2. Okay, so we can see right away here that we've got, oh, whoops, I've got x equals 2 is a 0, right? So that's helpful. It gives me 1 0, but it's a quartic. So what do I have to do then? Okay, good. I got to divide that through to see what the remaining cubic is. And then for the cubic, I'm going to be stuck with having to find the zeros with maybe the rational root theorem, right? At least one of them, okay? So if we divide this 2 in, what do we get here? 2, negative 8, negative 4, 8, and 32. And I'll just make a regular bracket for this one because I know it's a 0, right? I mean, I don't have to risk having to rewrite that bracket a bunch of times. So I already know that's going to be a 0. What are we getting here, though? So we get 2, 4, -4, -8, -12. You correct me if I'm wrong. -24, so that becomes a 16. Whoops, -16, -32. So it worked. Okay. So then we get the other polynomial. That's my constant, coefficient of x squared, x cubed, x to the 4th, x to the 5th, if they were there, right? So we're getting 2x cubed minus 4x squared minus 12x minus 16, right? And we're trying to find all the zeros, right? Okay. So now what? Now what do I do?
We'll list the numbers, like factors or whatever
From the rational root theorem. So I got to find all the factors of 16 over the factors of 2. Okay. Now when I do that, I'm going to show you something. When are we out of here? 53. Okay. I'm going to show you something kind of cool here. So we're going to get, if we come up with our list of zeros, or I mean of possible zeros, right? Factors of 16 over factors of 2. So isn't that going to give me the factors of 16? I'm going to get plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16, right? Okay, when I divide by the factors of 2, which are 1 or 2, well, I'm going to get all those. I'm going to get plus or minus 1/2. 2 halves is 1, 4 halves is 2, 8 halves is 4, and 16 halves is 8. So we only get one fraction out of that, right? Okay, could we have shortened that list just a little bit, though? We could, because we're trying to find the zeros, correct? Can I simplify that polynomial before I even start to find the zeros? Yeah, I could factor out a 2 and divide by 2, couldn't I? Right? If I divide both sides by 2, and I can even just write it this way, because I can divide both sides by a constant, by a number, that's fair game. So then I get the simpler polynomial, x squared minus 2, or x cubed, sorry, minus 2x squared minus 6x minus 8 equals 0. So what does that cut off of our list? It cuts off of our list a couple things. It cuts off the 1/2, which is nice. We don't want to have to deal with the 1/2. And it cuts off the 16, right? So it does shorten our list a little bit. Okay, now we'd have to run that through synthetically. Run these through synthetically and see which ones work. So we got 2 is one of them. Now we're going to find the others. And we can remember those, right? Plus or minus. Here, I'll just do this. I want to be able to scroll down. So okay, so there's my list. Oops. So my coefficients are 1, -2, -6, -8, and there's my remainder column, right? So let's try 1. Bring down the 1. 1 times 1 is 1, plus -2 is -1. 1 times -1, it's not going to work, is it? 1 times -1 is -1, so I'm going to get a -7, not going to work. So we cross +1 off of our list. Let's try -1. Let's see, so I got 1, -3, -2, not going to work, right? And check me if I make a mistake. I'm going fast. So that guy's off the list. Okay, let's try 2 again. We already tried, we used 2, but it could be a multiple 0, right? So we try 2. 1, 0. It's not going to work, is it? -6, that's not going to work. Okay, so we can cross +2 off our list. Let's try -2. So 1, -4. Not going to work, is it? Right? No, it's not going to work. Agreed? -2, -4, 8. Nope, not going to work. Okay, so we're on to the 4s. I got 1, 4. I think this is going to work, isn't it? 4, I'm going to get 2. Yeah, it's going to work. 8, so that's going to give me 2. And that's going to give me 0, isn't it? Everybody agree? So we got a hit. So 4 is a hit. And then we could just, we're going to run out of time, but that's okay. We don't even have to go through this last step because now we can use the quadratic formula here where that's A, that's B, and that's C. So my other zeros would just be -2 plus or minus the square root of 4 minus 4AC, so -8. We're going to get imaginary. We're going to complex conjugate pair, aren't I? Divided by 2. So that's just going to give me, let's see, I'm going to get a -1 plus or minus, and that's going to give me, what, negative I? Or a plus or minus I? Because I'm going to get a -4, right? Or 2I, sorry. Plus or minus 2I over 2 is just plus or minus I. I went really fast there because we're running out of time, but you guys get that? So I get, so there's 2, there's 1, and then my original one was a 2. So if we write all those down, I guess, my zeros were 2, 4, and 1, -1 plus or minus I. Okay? Good? All right. Well, we covered a lot today. Yeah, get your